Okay. Today I want to improve the power method. Here I only present the most basic algorithm. Okay, we don't consider many other details. Okay, take a review. For the most basic power method, we make the following assumptions. We assume the matrix A is a real matrix, not a compact matrix. And also we assume the matrix A has n linearly independent eigenvectors. Okay, these are the eigenvectors. Usually, a matrix may not have n linearly independent eigenvectors, but here we assume, okay, this matrix has n linearly independent eigenvectors, and the corresponding eigenvalues are λ1, λ2, and λn. And I assume λ1 is the largest eigenvalue in magnitude, in absolute value. Okay, in absolute value. We call this eigenvalue a dominant eigenvalue. Dominant eigenvalue. And this eigenvector, we call it dominant eigenvector. Right. So power method looks for λ1 and psi1. And also we further assume all the eigenvalues are real numbers. Okay. In general, a matrix is eigenvalue. Some are real numbers, some are compact numbers. Then how to find λ1 and psi1? The idea is arbitrarily pick a vector. Usually, in practice, we pick this vector randomly. Okay, and define the following iteration. Let me give a name to this. Okay, call it an iterate. Okay, so VK is an iterate, and it is easy to see that VK is A to power K times vector V. Now, how to find λ1 and psi1? Write the vector V. Write this vector, okay, as a linear combination of the eigenvectors. Okay, a C, review C. Okay, write vector V as a linear combination of the eigenvectors. Then apply A to K, the power of K, the power of the matrix, to the both sides of this equation. Cn AK. Because the side vectors are eigenvectors, so we have this equation: λ K1 psi1 and C2 λ2 K psi2 and so on. The Cn λn K psi n. Now take out λ1. Then we have C1 psi1 plus C2 λ2 λ lambda 1, then to k psi 2 plus cn lambda n lambda 1. By assumption, these ratios lambda 2 over lambda 1, lambda 3 over lambda 1, lambda n over lambda 1, they are less than 1 in absolute value. So when k is very large, we have AK times V. AK times V is the iterate VK. Roughly is equal to when K is large. In this sum, the first term is a dominant term. So roughly is equal to C1 times lambda 1 K psi 1. So when K is large, the iterate VK roughly is a dominant eigenvector. Right? Now the problem is from one example in the last class, we see that the entries of VK can be large or can be small depending on the size of lambda 1. If lambda 1 less than 1, then entries of VK very small. If lambda 1 greater than 1, then the entries of this vector can be very large. Okay, so we want to improve this situation. We want the entries of this vector not large and not too small. Okay, then how to do that? Normalize the vector. Okay, yeah, how to normalize the vector? Divide it by its length. Okay. This long is any vector long, usually too long, right? Or infinitely long, or one long. Okay, it doesn't matter. Okay, so yeah. So the idea to improve this situation is normalize the vectors. Okay. Okay, this is topic 1 today. Yeah. Okay, now topic 1. Topic 1. First, let eta 1 be the vector normalize the dominant eigenvector. The dominant eigenvector is psi 1. Okay, now over psi 1. Okay. And also let UK be the unit vector obtained by normalizing the iterate, the iterate VK by its law. Okay, now I want to prove the following theorem. The following theorem, not difficult to see. Okay, this is a theorem. Okay. This theorem has 2 parts. The part 1, if lambda 1, the dominant eigenvalue is positive, then we can prove UK defined here. When K approaches infinity, the limit of UK is equal to when k approaches infinity, uk will approach eta 1. But there is a sign in the front, psi n of C1. C1 is here, the component of the vector v in the psi 1 direction. Okay, yeah, this C1 here. Okay, psi of C1 times eta 1. What is the psi function? Let me show you some examples. Psi, say for example, a positive number, say 38. The value of the sign is 1. A psi of 0, it is 0. Psi of a negative number, say 100 negative, it is a negative 1. Yeah, this is the definition of the psi function. Yeah. Case 1. Now, second case. If the dominant eigenvalue less than 0, then we have a limit k approaches infinity. -1 to k times u k times this vector, this unit vector. The limit is psi C1 times eta 1. Eta 1. Okay. Now let me first prove this theorem. How to prove? How to prove? Okay. We first set, go back to here. Go back to here. This is VK. VK. Let me move this number to the left side. We first set WK be VK over lambda 1K over lambda 1K. So this is equals to, yeah, from this equation. I move this number to the left side. Then VK over lambda 1K. I set in WK. That WK is equal to this. Yeah, equal to this. Yeah. So this is C1 psi 1 plus C2 lambda 2 over lambda 1 K psi 2 plus Cn lambda n over lambda 1 K psi n. Because the ratios are less than 1 in absolute value, then when I let k approach infinity, the limit as k approaches infinity, this vector, the limit is exactly this. Okay, C1 psi 1. Okay. Now from this equation, we further have the log of WK is equal to the log C1 times psi 1. Move C1 out at absolute value on C1, then times psi 1 in log of psi 1. All right, now after we have this limit, and this limit, these two limits, I can prove part A and part B. Now take a look at part A. Let me erase here. Okay, now part A. Part A. In part A, I assume lambda 1 greater than 0. The limit as k approaches infinity, uk. By definition, uk is this. Vk over the ln of Vk. Then I make UK into WK. So I divide the numerator by lambda 1k and divide denominator by lambda 1k. Because lambda 1 is positive, so I can move lambda 1k inside the ln. Inside the ln. The top is Vk over lambda 1k. Okay. Now I can move it, move lambda 1 inside the ln. Yeah. So we have limit k approaches infinity. Vk over lambda 1k by definition is wk. So this is a wk over the ln of wk. So the limit is as k approaches infinity, wk approaches c1 times psi 1. So c1 psi 1. And the ln of wk approaches absolute value c1 times the ln of psi 1. Psi 1. So c1, a real number, c1 divided by absolute value of c1 is psi of c1. And psi 1, this vector divided by its ln, by definition, eta 1. So eta 1. Eta 1. So I prove part A. Yeah, I prove this equation. Okay. Now part B. Part B. B. The limit as k approaches infinity, let the 1 k uk is equal to let the 1 k uk is vk over the ln of vk. Then I divide the numerator by lambda 1k, denominator by lambda 1k. Okay. Okay. Now combine -1 to k and this lambda 1k. Over lambda 1k. Then this is a vk over negative lambda 1k. Here in part B, I assume lambda 1 less than 0. So negative lambda 1, a positive number. this is a positive number, so I can move it inside the law, the vector law. Yeah. Negative VK, then over lambda K, right? I can move this positive number inside the vector law to get this. Okay. So this is a limit K approaches infinity. Yeah. The top is WK by definition. Then the bottom is negative WK. Yeah. So negative WK has the same norm with WK. Same norm with WK. So we have the limit is WK approaches WK approaches, let me see. Oh, C1 psi 1. So this is a C1 psi 1. And the norm of WK approaches the absolute value of C1 times the norm of psi 1. So absolute value psi 1. So again, C1 over its absolute value is psi of C1. And psi 1 over its norm by definition is eta 1. Eta 1. So I prove the second part. Yeah. I prove this limit. Yeah. The second part. Yeah. This limit. Yeah. This theorem says that okay, from this theorem, from the theorem, okay, when K is very large, part A assume lambda 1 greater than 0. Okay, part A, when K is very large, UK, yeah, UK, roughly is this. UK roughly is psi C1 times eta 1. Eta 1 is dominant eigenvector over its norm. But psi 1 is a number, norm is a number. So a number times an eigenvector is still an eigenvector. So when K is very large, so when K is very large, this vector is about roughly a dominant eigenvector. A dominant eigenvector. Part B, we assume lambda 1 less than 0. From this limit, when K is very large, this roughly is this. Okay. From part B, lambda 1 K UK roughly is psi C1 times eta 1. Now from here, I move the psi negative 1 to K to the left side. So UK roughly is negative 1 K times psi C1, eta 1. But eta 1 is psi 1 over the ln of psi 1. Again, this is a number, and a number. A number times a vector, eigenvector, still an eigenvector. So UK is also roughly is about a dominant eigenvector. So in both cases, UK, when K is large, they are roughly eigenvectors. Okay, yeah. So based on this observation, we have solved the problem about eigenvector. How about eigenvalues? Okay, eigenvalues. How to find eigenvalue? The dominant eigenvalue lambda 1. Okay, and also two cases. Okay, eigenvalues. Case 1, A. Assume lambda 1 greater than 0. Now from the theorem, as K approaches infinity, UK, the limit is psi C1 and eta 1 from the theorem. Okay, now let me multiply matrix A on the both sides. Then this implies that limit K approaches infinity, A times UK is psi C1, A times eta 1. Eta 1 is an eigenvector corresponding to lambda 1. So this is a lambda 1 psi C1 times eta 1. Psi 1 is an eigenvector. Okay, now from here, take one entry, say entry I. Okay, yeah, A times UK, the ith entry over the ith entry of UK. Then limit the ith entry of A times UK. The limit is lambda 1 from this equation. Lambda 1 psi C1 times the ith entry of psi 1. Psi 1 and over the ith entry of UK by this equation. It is psi C1 times the ith entry of psi 1. Now cancel this number and this number. Then we have lambda 1. So we can find the dominant eigenvalue by consider some entry of A times UK over some entry of UK. Yeah. This is a case. The case when lambda 1 greater than 0. The second case is similar. Second case, when lambda 1 less than 0, then by the definition we have this limit. The limit as K approaches infinity, negative 1 to K times UK is equal to psi C1 times eta 1. Now multiply this equation from the left side by the matrix A. We have this equation. Sine C1 times A times eta 1. But eta 1 eigenvalue, eigenvector. So it is a lambda 1 sine C1 times eta 1. Hey, now again, consider some entry. A times UK. The ith entry over UK. The ith entry. Take limit. Let me see. The limit should be lambda 1, but how to see this limit is lambda 1? Let me multiply the top by negative 1 to k. And also multiply the bottom by negative 1 to k. But this limit is from this equation here. This limit is from this equation. The top, the limit is lambda 1 sine C1 times the ith entry of eta 1. The bottom, the limit is from this equation sine C1 times eta 1. The ith entry of eta 1. Okay, now let me cancel some numbers. Cancel this number, and this number. So therefore, it is lambda 1. So in either case, lambda 1 greater than 0 or less than 0. A times UK. Take the ith entry over UK. Take the ith entry. The ratio approaches lambda 1. Lambda 1. Okay. Now we are ready to write down the following algorithm. Okay. Now algorithm. This is an improved version of the power method. Okay. Yeah. Algorithm. Yeah. Second algorithm. Algorithm. Okay. Okay. Step 1. Pick a vector. Usually, arbitrary pick, randomly pick. Okay, pick a vector. Then set U0. U0 by definition is a V0 over the norm of V0. Now V0 is vector V, so V over the norm of V. Yeah. Right, now second, pick an index. Pick an index I. Okay. Of course, I is between 1 and n for the computation of the dominant eigenvalue. Okay. Okay. Now second. Now perform a for loop for k 1, 2, 3, and so on until convergence. Okay. For k from 1, 2, 3, and so on, we compile the following iterate. compute U K is equal to A times U K minus 1. Okay. Then compute eigenvalue lambda K. Lambda K is A times U K minus 1. A pick is I entry, then over U K minus 1. Pick the I entry. A times U K minus 1 is UK here, UK. Then over U K minus 1. Yeah, compute eigenvalue. Then the final step, normalize the vector UK. UK, set UK to be UK divided by its log. Make UK into an unit vector. Okay, then and the follow. Okay, yeah, this is the second version of the power method. Okay, now let me show you one example. Still, I pick the matrix from the example I presented in the last class. Example 1. The matrix in the last class. Let me find out the matrix from the last class. Matrix A is a 3 by 3 matrix. And the exact eigenpairs, lambda 1 is 3. This is the dominant eigenvalue, and corresponding eigenvector is this. The second eigenvalue, -2. Corresponding eigenvector is 0, 1, -1. And the third eigenvalue, 1. And eigenvector is now this time I compare this eigenvalue and 1 corresponding eigenvector by the new version of the power method. Okay, now let me make a table here. Make a table. In this computation, I said the same. The vector V to be 1, 0, 0. And take I to be 1. I to be 1. That means that I use the first component of the iterates to compute lambda 1. When K is 0, UK now is a unit vector. It is a vector V over its log. This is a 1, 0, 0. Lambda K. When K is 0, we haven't compute lambda K. When K is 1, UK is negative 0.3015, the first entry. Negative 0.045. Then lambda k is 1. So lambda 1 here is the first entry of U1 over the first entry of U0. So it is why it is a negative 1. Let me see. It is a times U k is 1. K is 1. K is 1. So a times U to U0 over U0. I is 1 here. I is 1. So this number is negative 1. Negative 1. Yeah. When k is 2, 0.2335, 0.3669, negative 9005. It is 7. Why it is 7? This number over this number shouldn't be 7, but maybe I made mistake in my notes. No, should be this number over this number. Okay, shouldn't be 7. Okay, yeah, this number over 1 should be shouldn't be negative 1. But here, yeah, this column I made mistake in my notes. But anyway, continue. Then when k is 11, because UK is a unit vector, so the entry is not too large and not too small in general. So it is a 0.3028, 0.2993. Yeah. So yeah, the last column. Remember, I made mistake. Okay. Yeah. So I should correct the data in the last column in my notes. Now, when k is 12, we get this number. 0.9043. And then lambda very close to 3. Now, from the eigenvalues, we can tell, okay, the approximation is good enough. So we pick this vector as the dominant eigenvector. This vector should be some scalar, okay, some scalar C times this vector. Yeah, some scalar C times this vector. Yeah. So yeah, this time the second version, okay, keep eigenvectors not large, not small. So computationally stable. The first version not stable. Yeah, the entries of UK go up to infinity. The first version. Yeah. This is about the power method. There are some variants that I should mention here. In the algorithm that I describe here, the algorithm compute the largest eigenvalues and its eigenvectors. But if you want to find the smallest, how to find the smallest eigenvalue? Say lambda n. How to find? this time, take inverse on A. Inverse on A. This matrix eigenvalues is eigenvalues are 1 over lambda 1, 1 over lambda 2, and 1 over lambda n. But now lambda is the smallest. Now 1 over. So this is the largest eigenvalue. The largest eigenvalue. So apply the power method to this matrix. Then we can get the smallest eigenvalue of the matrix A. This is a one variant of the power method. Now, second variant of the power method. All right. How about if I want to find other eigenvalues? In this case, take a number, mu. Okay, mu. This is a number mu, a real number. Then consider this matrix A minus mu times I. Then take inverse. This matrix its eigenvalues are 1 over lambda 1 minus mu, 1 over lambda 2 minus mu, and so on. 1 over lambda k minus mu, 1 over lambda n minus mu. Suppose say lambda k is the closest eigenvalue to mu. Then when we apply the power method, to this matrix, okay, then the power method will find this eigenvalue. Yeah, and if lambda k is the closest eigenvalue to mu, then 1 over lambda k minus mu is the largest. Then power method will find this number. Okay. After we find this number, then we can solve for lambda k to get lambda k. That means that apply the power method to this matrix, we get the eigenvalue lambda k of the matrix A. That is the closest to the real number mu. Yeah. These are two variants of the power method, and we give a name to this method. We call it inverse power method. Yeah, inverse power method looks for the smallest eigenvalue. How about this method? We call it, give a name, shifted inverse power method. Yeah, shifted inverse power method look for the eigenvalue of matrix A that is the closest to this real number mu. Okay, mu. Okay, now let me stop here. On Friday, we will learn QR method. Yeah, QR method find eigenvalues, all the eigenvalues of matrix A simultaneously. The power method just find a single eigenvalue. Now QR method find all the eigenvalues at the same time. Okay, yeah, that is the story of Friday. Today, let me stop here.